Okay, welcome to my channel Fakruddin Academy Physics, my dear students. Today I would like to discuss a very beautiful chapter and the first class of your physics crash course for Neet and Jee mains. And this inshallah will continue. Okay, for 60 days I am planning to continue this course here, okay, so that everyone can benefit without paying any fees. Even the poor students can get benefit from my classes. Thank you very much. So all of you see here now. Let me discuss about the first topic of this class, that is called as photoelectric effect. So what do you mean by this photoelectric effect? Photo means it is related to photons. You just remember that fact. Photo means that is related to photons. So from the sun, photons will come out. And you all know that the energy of each and every photon is given by h nu according to Planck. Energy of every photon is given by E is equal to h nu, because energy is directly proportional to frequency. If you remove the proportionality, you'll get a constant which is called as Planck's constant, h. And here, as soon as the photon falls here, there are metal plates like potassium, calcium, like this. Metal plates you can consider, any metal plate you can consider. So you are taking a metal plate. The radiations coming from the sun, they fall on the metal plate. And you all know that metals are having millions of free electrons in that. Metals are having millions of free electrons in that. And these free electrons will get sufficient energy to come out of the metal plate. And the energy required to remove the electron from a metal plate are work done by the electromagnetic radiations. When they fall on the metal plate, they will do certain work to remove the electrons from the metal plate. That work done is called as W naught, which is called as work function. We call it as a work function. What do you mean by work function? The minimum work done to remove the electrons from the metal plates when electromagnetic radiations fall on the metal plate is called as work function. And now once the electron comes out from the metal plate, they will get a lot of energy which is called as kinetic energy. As we are connecting high potential here, and this is a glass bulb which is evacuated glass bulb. In this evacuated glass bulb, no air is present in that, because it is evacuated, means the air present in the glass bulb is also removed out and only vacuum is present. It is done so that the electrons, when they rush towards the positive terminal, because we are connecting the positive terminal here and negative terminal here. So from negative terminal, when electron moves out, when they move very fastly with high kinetic energies towards the positive terminal, then air should not act like a friction. Air should not act like a viscous forces to stop the electrons, or to be on the way of an electron, so that electrons will move very fastly towards the positive terminal here. And the electrons, when it rushes towards the positive terminal, the electron starts moving towards the positive terminal in a wire. And you know that a current is produced. So ultimately, the energy coming from the photon is converted into electrical energy here. And this total process, in which light falls and it divides into two parts, that is, energy coming from the sun is taken as h nu. It is divided into two parts. The first part is taken as work function, work done to remove the electrons from the metal plate. And the second part is taken as maximum kinetic energy. So energy coming from the sun is divided into two parts now. First part is the minimum work done to remove the electrons from the metal plate. And the second part is the electrons will gain high kinetic energies to move towards the positive terminal, so that it can constitute the current. And the current produced in this case is called as photoelectric current. Photoelectric current is produced. Now, let us see what is going to happen. And this equation is called as photoelectric equation. Energy, that is h nu, W naught. What is W naught? Let us discuss about that. So E is equal to h nu. W is nothing but h nu naught. Okay, then let me discuss about what is nu naught here. See here, nu naught means it is called as threshold frequency. It is called as threshold frequency. Now let me discuss what is the meaning of threshold frequency. In dictionary, when you see the meaning of threshold, the minimum value at which something happens. In dictionary, if you see the meaning of threshold, the minimum value or minimum point at which something will happen here. But what is threshold frequency? The minimum frequency at which something should happen here. What is going to happen here? The minimum frequency at which the electrons will come out from the nucleus. It is becoming detached from the nucleus, or it is detached from the metal plate and they come out. So that frequency is called as threshold frequency, at which electrons becomes free from the metal plate and they come out. They will get sufficient energy. That frequency is called as threshold frequency. So now, and this is taken as kinetic energy maximum, which can be written as half m v maximum whole square, because electrons are having maximum velocity at this place, so that they can rush towards the positive terminal. So now what are you going to do? Let us see here. Now we have to find out what is V maximum here. So to find out V maximum, you will write V maximum is equal to H common out nu minus nu naught. 2 will come and m will come at the denominator, and you will make it a square root of this. So square root of 2 H by m nu minus nu naught. So this is the formula to find out the maximum velocity of the electrons which are rushing towards the positive terminal in this case. So this is a complete photoelectric equation we are getting now. Now, if you want to simplify this equation a little bit, let us see what we are going to get now. We all know C is equal to nu lambda. Velocity of light is equal to frequency into wavelength. Then nu is equal to C by lambda. Similarly, we can also write here C is equal to nu naught lambda naught. Velocity of light is not going to change. If at all something is changing, frequency has to change and wavelength has to change. So nu naught lambda naught. Lambda naught is called as threshold wavelength. As we are writing the formula C is equal to nu lambda, nu is equal to C by lambda, then we will write C is equal to nu naught lambda naught. So from this you will getting nu naught is equal to C by lambda naught. So we got the formula for nu, we got the formula for nu naught as C by lambda naught. If you substitute the values here, your formula little bit changes like this. So 2h by m, nu can be written as C by lambda, and this is C by lambda dash. Here you can common out C and you can write V maximum is equal to square root of 2hc by m 1 by lambda minus 1 by lambda dash. You can also simplify this as 2hc by m lambda naught minus lambda. So in this way you can simplify the equation and write it. So this is the formula for maximum velocity. Okay, so let us discuss about the graphs here. So intensity, the light coming from the sun is having certain intensity. Morning intensity will be less, in the afternoon intensity will be more, and in the evening intensity reduces. But what is this graph showing here? The greater the intensity, the greater is the photoelectric current. The greater the intensity coming from the sun when it falls on the metal plate, high intensity light coming from the sun falls on the metal plate, produces more free electrons. The metal plate will get highest value of intensity from the sun, and it produces more number of free electrons. When the electron number increases, electric current also increases. So photoelectric current and intensity is directly related. So as the intensity increases, photoelectric current also increases, which is going to give you a straight line graph. And this graph represents that both are directly related. So intensity and electric current, photoelectric current, they are directly related. Now let me discuss about this graph here, which is showing the potential we are going to apply here, and this is photoelectric current in the y-axis. So what is this graph explaining here? As soon as the sunlight falls, the electron number increases and electric current also increases, but after a certain time the graph shows constant line, a straight line with respect to y-axis. That means at this place saturation point has reached. So this is called as saturation current along the x-axis. Along the x-axis potential is there, and along the y-axis photoelectric current is there. First, as soon as the sunlight falls, current slowly increases, and after a certain point current becomes maximum and it is not going to increase, and that maximum current is called as saturation current. So once it reaches to saturation point, there is no chance for current to increase. Okay, so this is the total diagrammatic explanation and also graph here. But what about this negative graph? If you just interchange the terminals, let us see what is going to happen. Now suddenly, when on the way the electrons are trying to rush towards the positive terminal, meanwhile you have just changed the terminals here. Now this is going to be negative and this is going to be positive. Suddenly when the plate becomes negatively charged here and this is going to be positively charged here, what happens? The fast moving electrons, they will stop. As if disc brakes are applied to the electrons. Because this is negative, electrons also negative. Because of repulsion of same charges, the electrons will be opposed to come towards this terminal, negative terminal. These negative terminals will try to push the electrons, will try to apply the brakes on the electrons which are rushing towards the terminal. Then suddenly, slowly, the photoelectric current will decrease in the negative. So this is minus V0 and this is plus V here. Okay. So this is minus V and this is plus V here. This is positive terminal. If you're connected, the graph will be like this. And when you change the terminals like this here, negative terminal is connected to the this right side plate here. Suddenly, the electrons which are rushing towards the positive terminal, their velocity will decrease and they will come to rest and they will never touch the metal plate. So slowly, electrons moving towards this terminal decreases its speed, and as the potential is increasing here, the potential at this negative sense, it goes on increases, electric current goes on increases, goes on decreases here, goes on decreases, and slowly all the electrons will be stopped here at certain fixed potential. At certain potential, slowly if the potential, negative potential is increased, the point will be reached, which is called as stopping potential, at which photoelectric current becomes zero because of repulsion of same type of charge on the electrons, which are negatively charged. So slowly this potential is called as negative potential, and this is called as stopping potential. So what is the meaning of stopping potential then? The potential, the maximum negative potential at which the photoelectric current becomes zero is called as negative potential. Okay, so I think you have understood this graph also. Now let us discuss about the next graphs here. So my dear students, already we have discussed about photoelectric equation. Now let me discuss about how to change this equation in terms of stopping potential. For that, already we know this is a photoelectric equation. But as soon as you interchange the terminals, electrons which are having high kinetic energies, they are going to stop. And they are going to stop because of same type of charges here. Then what is going to happen here? Kinetic energy, as it is directly proportional to stopping potential. That means high kinetic energies are converted into potential energies now, because we are applying the same type of charges. You all know that energy can neither be created nor be destroyed, but it can be changed from one form to another form here. So kinetic energy is converted into potential energy. That means half mv square is changed into potential energy, that is nothing but work done. And you know work done is a product of V into Q. You all know work done is nothing but it's a product of V into Q. And you all know that electric potential is nothing but work done on unit charge. Work done is nothing but potential into charge here. But as we are considering the stopping potential at this place, we will consider the stopping potential as V naught. So now we can change half mv square, that is V maximum whole square, into V naught into E here, or V naught into Q here. Okay. So this is a small change we have to make here. So kinetic energy has to be converted into potential energy. Then your equation is going to become h nu is equal to h nu naught plus V naught into Q. And if you want to find out the stopping potential, then you have to do like this. So V naught is nothing but h nu minus nu naught when you transfer here divided by Q. Okay. Then if you want to find out the stopping potential h by Q, you know that nu is nothing but C by lambda and nu naught is nothing but C by lambda naught. Already we have discussed about this. Then you can write stopping potential as hc by Q 1 by lambda minus 1 by lambda naught. So this is the formula for stopping potential here. So this is the formula for stopping potential here. So stopping potential, if you want to find out, you have to write hc by Q 1 by lambda minus 1 by lambda dash. Now let me discuss about the remaining graphs, which are very important while solving the conceptual questions of NEET and JEE mains. So if you consider this as a graph here, so potential is represented along the x-axis as usual, and current is represented along the x-axis, along the y-axis here. But the graph shows a little bit different concept here. When the intensity of light coming from the sun is high, then high intensity photons, when it falls on the metal plate, the population of electrons oozing out of the metal plate, coming out of a metal plate, is very high. When population increases, current also increases, because current is nothing but rate of flow of charge. The more the electrons, the more the flow of electrons, the greater is the electric current, which is called as photoelectric current. So what I'm going to say here is, when intensity increases, this saturation current also increases. Saturation current is also going to increase. So I1 represents the intensity which is a little bit lesser. So saturation current is less here. But as the intensity increases, I1 is less than I2. So I2 is greater and less than I3. I3 is maximum. So when maximum intensity coming from the sun, let us take in the afternoon. Sun is having maximum intensity in the afternoon. It is exactly above us at 12 p.m. So now when sun is having high intensities, more number of free electrons comes out, more kinetic energy, more current. So what I'm going to say here is, greater the intensity, greater is the saturation current. But intensity is independent of stopping potential. So when you take in the negative direction, negative potential in this direction as minus V. When you reverse the terminals here, so the diagram shows that stopping potential is same for different intensities of sunlight. Even intensity is more, stopping potential is same. In the intensity decreases, stopping potential is same. So we can write stopping potential is independent of intensity. Independent of intensity of sunlight. Now let me discuss the next graph here. So frequency of incident radiations. So you know that sun is having certain frequency of incident radiations. So the frequency of incident radiations at which the electrons are coming out is called as threshold frequency, which is represented with mu naught here. The minimum frequency required to remove the electron, the minimum work done to remove the electron from a metal plate That frequency is called as threshold frequency. That is taken as nu naught. So here kinetic energy is directly proportional to stopping potential. And when you take the different metal plates here like calcium, potassium, sodium, their threshold frequencies are different. For calcium, threshold frequency is less. So this is x-axis showing a frequency of incident radiations. Frequency of incident radiations, and that is equal to nu naught. So this is stopping potential V naught. So for calcium, this is said to be a frequency of incident radiation nu naught, which is frequency is equal to frequency of stopping potential here. Then electrons will come out. For sodium, frequency is different. Frequency required is different. For potassium, frequency required is different. So stopping potential or threshold frequency, the minimum frequency required to remove electron is different for different metals. And you can say it is maximum for sodium. Potassium it is little bit lesser, threshold frequency is little bit lesser. And for calcium it is still lesser. So this is a graph showing a straight line that frequency of incident radiation is directly proportional to threshold frequency. Okay, so frequency of incident radiation. Frequency, what does it mean? Number of waves passing per second is called as frequency. Let me draw one graph. So this is a graph which is showing that the waves are having high frequencies. This is a graph which is showing that the frequencies are lesser. So greater the frequency means number of waves passing per second are more. Lesser the frequency means number of waves passing per second are less. So this is a graph regarding stopping potential and frequency of incident radiation. Now let me show one more graph. Here this graph shows that potential is along the x-axis, again current is along the y-axis here. That is called as photoelectric current. So in this case, frequency is directly proportional to stopping potential. What does it mean actually? So when the sun rays having high frequencies, when they fall on the metal plate, the electrons will gain higher kinetic energies. So greater frequencies creates higher kinetic energies. So when higher kinetic energies are present, we need higher stopping potentials, because to compensate that high kinetic energy, we have to supply high potential, which is called as stopping potential. So what I mean to say is, when sun rays of high frequencies falls on the metal plate, the electron will gain more kinetic energy. They rush towards the positive terminal with higher kinetic energies. And to stop that high kinetic energy electrons, we need higher stopping potentials. So therefore, stopping potential goes on increases when frequency of sunlight increases. But you can observe one thing here. That is, saturation current is same for all types of frequencies coming from the sun. So with this, we will get a sentence that frequency is directly proportional to stopping potential for different frequencies, but frequency is independent. We can say it is independent of, frequency is independent of saturation current. Okay, so we getting saturation current here, saturation current. So even though you change the frequencies, but saturation current is same for all the frequencies, whereas saturation current is depending upon the intensity, not on the frequency. Intensity increases, saturation current increases. Frequency increases, saturation current does not increase, but stopping potential increases because of high kinetic energies in the electrons. Hope you have understood this concept of photoelectric effect. This is a complete idea of photoelectric effect. I think you have understood this concept easily. So thank you very much. Let's go for the next video.